And I decided here that it's going to stop at 0.3. Right, when you do take a risk of, in the assignment, you've got to work out a risk of, how bad is it to get caught cheating? Right? If you cheat, then you're taking a risk about whether I get caught cheating. You've got to work out how many marks is it worth to me, right, to take a risk. So you think about how bad it can be, and you think about how good it is, and then you take risks. And the medical doctor, they think about how bad it can be and how good it is, and they take risks. They've got to choose somewhere in the middle about where they're going to trade things off. And then we're going in the scale, we're then going to place W0 is, so W1's sort of way up here, right? W1's actually pretty good. It has some, so then we're going to place all of these somewhere in here. So we're not willing, it's not worth exactly W5, but it's pretty close, right? Because we're not willing to give it up. We don't want to take much of a risk of getting the worst outcome. And then we're going to scale all of these in between this. Okay, are there any other questions about this? So what we're going to do is we're going to try and, once you do an example, it makes a whole lot of sense. So in the assignment, there's an example of people trading off someone who really wants to get an A and really wants to get an A and is willing to do all sorts of work to get an A, and someone who just wants to pass, then they're having different risk assessments. This is non-trivial. When the turn of the century, Time magazine had this thing about what are the greatest inventions of the 20th century, and utility theory, I think, came out as number 3 or 4. So this theory that says that we can really trade off between these lotteries and things because it's sort of the basis of economic decision theory, because you can mix them with probability, and things get to be nice mixes of making decisions. And it's really the basis for all of these decision-making under uncertainty, where we have to actually make decisions. We end up thinking about utilities in terms of lotteries and trading things off because we're worrying about uncertainty because we're taking risks in here. Okay, any other questions? All right, I'll fix these up. Later on, we're going to do utilities can be any real number, and we're just going to scale them to 0 and 1. So often we're actually going to use 100. Often we use 100. Often we're going to multiply all these by 100 and then use 0 to 100. And sometimes we talk about in costs and we end up having negative numbers. But they really mean the same thing. We're just scaling them onto this. And it should become pretty obvious about how that works. Right, because there's no real reason. So sometimes want to use a different scaling factor to probabilities. Just say them from 0 to 100, and then we talk about percents. And the whole thing doesn't matter here about what else scaling is. Because we're only really going to use one utility value, whereas we're going to multiply lots of probabilities. They sort of have to obey the 0 to 1 rule, but these utilities, we're only going to use one utility model for any decision. And different people can have different utilities. So part of research people are doing, we've been working for, we had some studies where people were working out the wastewater for the new building, the Vanier building, and we had people sitting there and arguing about the utilities or the cost-benefit trade-offs for all these different options for putting wastewater. And then we had people sitting there and arguing about what the utilities should be. So, because this one, we could actually argue about what's important and what's not important, and how important is it. We could trade things off, and we could put things into decisions. Then we say, if these are your values, here's what decision you should make about the wastewater. Okay, so we're going to do things like that. So the other one is expected. The other thing we need to build this theory is expected value. The expected value of a function of possible worlds is average valued, weighting possible worlds by the probability. So we're going to, if f of w is the value of function f on world w, the expected value is, we're going to write this funny e of f is we're going to sum over all the worlds the probability of the world times the f of this world. Right, so if we have, here's the simple example. If we have the roll of a dice and you get the value on the dice, if it's odd, and you get -1 if it's even, what's the expected value? Right, so you've got these two things. You roll a dice, you get this value on the dice, you get -1 otherwise. What's the expected value? Is this something people know how to compute? Right, you get, right, so it's 1/6 times, it could be a 1, which is you get 1, you get 1/6 times -1 plus 1/6 times 3 plus 1/6 times -1 plus 1/6 times 5 plus 1/6 times -1. Right, so here's all the outcomes. This is all the probabilities of these outcomes. And here's the value of that outcome. Right, so this is what we did. This is the outcome. You get a 1. You get 1, you get a 2 is rolled, you get -1. If 3 is rolled, you get 3. If a 4 is rolled, you get -1. If a 5 is rolled, you get 5, 6. So it's just the probability times utility. And if someone tells us that it's less than 5, if the given the outcome is less than 5, we're going to end up just ruling these two out. And we end up with each of these as a probability a quarter. So we get a quarter times 1 plus a quarter times -1 plus a sixth, a quarter times 3 plus a quarter times -1. Right, so we only look at those worlds where this is true. So that's just expected values is something I think you probably, just the average value weighted by the worlds. Okay, it's I think something you'd probably, all right, so any questions about that? So now let's stick everything together. So we're going to have we're going to look at first we're going to look at single decisions today, then on Wednesday we're going to look at multiple decisions when we're going to make sequential decisions. So an agent makes all the decisions before acting in this case. And you've got to choose the value for each decision variable is what's going to happen. And we're going to combine all the when we do this theory, we're going to just combine all the decision variables into a single variable D. And then the expected utility of decision D is the expected value of U, where U is the utility function. So U is this function on worlds, is the utility function, or the expected utility given this decision. Remember, I only had utility defined when we were actually conditioned on the decision. And the optimal decision is the decision D max, whose expected utility is the maximum. So I'm going to choose the decision D max. I'm going to choose to do D max such that that's the maximum of all of these other values. So I'm going to choose the maximum thing I can do. So I'm going to try and choose the maximum decision I'm going to do. And so then we're going to end up extending our our belief networks to include these other things. So we're going to include decision nodes. We're going to use these as rectangles. The agent gets to choose the value of these. The range of these is a set of possible action. We're going to draw this as a rectangle. So we're going to choose, the agent here gets to choose whether it wear pads. It gets to choose which way it goes. And it gets to, then there's an accident here. This says the probability of the accident only depends on which way you go. But the utility depends on whether you wear pads, which way you go, and whether you have an accident or not. Okay, so we have the utility nodes. Here, the parents are the variables on which the utility depends. I'm going to draw that as a diamond. So we have, so The random variables are those ones we did before. And this explicitly says that which nodes affect the accident. So this says whether you wear pads, whether the agent wears pads or not doesn't affect whether it has an accident. Right? So now we've got to choose a value for wear pads, choose a value for which way, such that we're maximizing this expected utility. And that's what we're going to try and do with these things. So in here we have a directed acyclic graph with three sorts of nodes. There are decision nodes, there are these rectangles, there are random nodes, and there's one utility node. The range for the decision, there's a range for the decision and the utility nodes. There's not a range for the utility node. That's just going to be some real valued number. So there's only going to have one utility node, we're assuming. And for now, we're going to assume that all decision nodes come before all random nodes. Now we have a conditional probability table for each random variable given its parents. We have a utility function depends on the parents of the utility node, and there are no tables associated with the decision node. So in our tool that we've been playing with, we can just add these in. So we end up where are wear pads, which way, with the utility. We're going to end up with a function here that tells us just this is the same thing we've always had before. It just says which way. Whether we go short or long, we have an accident. So if we go the short way, there's a probability of 0.2. And if we go the long way, there's a probability of 0.01. So now we have this, just the normal way we did for Bayes nets. We're now going to extend it to these decision networks. There's the table for the utility, which is just going to be this one down here, the one we drew there. We're going to have the best outcome here was that we didn't have an accident, we went the short way, and we didn't wear pads. The worst outcome is going to be this third one here. We went the long way. We had an accident, we went the long way, and we didn't wear pads. And then we scaled each of those in between there. So there's this one table for this decision node. And there are no tables for decision nodes. Right? We don't get to choose the value of it. There's no table associated with these things. The other thing to notice about this is that we actually have a value for each value for accidents in here. So it just depends on for each one of the parents, we get to have a distribution over where we have an accident. But the utility node is sort of different from that. There's no distribution over utility. There's just a utility for each value for the parents. So there's just this function that says which way we're going to go. Okay. All right, so now we have this little modeling language. We can model decisions. So now what we'd like to do is we'd like to select values of the decisions in order to work out the expected utility in here. How do we have for time? We've nearly finished. Okay. So what we can do in here is, so one of the things when we solve this, solve this node. So let's just do brief. So what we can do is if we viewed this expected utility, we actually end up with computing some average value in here. So the average value is 83. And what it did was it actually assigned a value. So it said when we're wearing pads, it said we should go the short way is the optimal thing in here. It's going to choose a value for the decision node which optimizes it. And it's going to choose the value for whether we wear pads. So the answer here is it's going to wear pads. The optimal decision here is to wear pads, and here and to go. Whoops. So the optimal decision is to wear pads, and we can actually look at the utility. Let's look at the utility function. We get an expected utility. We can look at the probability of an accident like we did before, and we can change our decision. So we could say when we wear pads, we'd like to make it, if If I don't wear pads, it's going to change. The expected value is going to be 80.6. So if I change this decision, I'm going to change the utility. Okay, if I change this decision lets me change it, so I can now change it for it to go long, whichever way this other one goes, and again to 79. Right, so if I went, so for each assignment of wearing pads and utility, we have a probability of an accident and the utility changes. And what we're going to do is we're going to try and, the problem now is to choose values for these decision variables that maximizes our expected utility. Okay, so we get to choose these. Right? We get to choose this, which one we do here, and now we're going to, for each of these values, the same our calculus we did before, computes expected values, and want to maximize our decision. So let's stop there.